Is Todd Owen. He is employed by the WA Health Department, where he helps develop systems to link data for public health research. He's engineered most of the testing and continuous integration practices currently used by his team and can't imagine life without automated testing. Please make Todd welcome.
Good afternoon. Now, I know everyone is probably feeling like a short nap after that lovely big lunch, but remember why you're here. You're excited about PyCon. You're excited about Hobart, and most of all, you're excited about testing. Just like these three girls chasing down bugs, I am excited about testing. Okay, so who am I? Well, Russell went into that. Anyone else here from Perth, by the way? Oh, lots. So I work on software at the WA Health Department for standardizing and matching data about people from disparate collection systems. So I can tell you it's a dirty job. We see a lot of dirty data. Why am I excited about testing? Honestly, it's the same thing that got me into programming in the first place. I love solving problems. What I don't like is spending half a day writing a long, ugly test method that calls half a dozen supposedly private member functions, and then a week later it breaks because some dependency somewhere has changed. Is that problem solving? I call that creating a problem. So for the purpose of this presentation, when I talk about problem solving, I'm not talking about the business problems, and there are other talks at this conference about that. I mean that test design is a problem worth solving. And the best way of writing and organizing tests is going to be different for every project. So choose your weapons carefully. Just because someone has built a better mousetrap doesn't mean it's the best way to catch butterflies. Let's start with a quick example. You've got a function you want to test called getLatestTweet. It takes a Twitter username and returns that person's most recent tweet. Please just take 10 seconds to think about how you might test that. There are actually lots of ways you might approach it. If you know the other objects that it collaborates with, you could use mocks. If you want to test all the way down to the network layer, or you could write a fake Twitter server that gives some canned responses. Or alternatively, you could record a session connecting with the real twitter.com and then replay it during your tests. Or if you happen to have a full implementation of a Twitter server, you can spin up a private test instance and connect to that. Or even connect to it in memory so that you don't even rely on the network. Or you could create a real Twitter account, then log in and post one tweet and then don't touch it again. Later, when you run your tests, you'll always be able to get the same result. Now, all of these have pros and cons. They don't necessarily serve the same purpose even. So connecting to a real Twitter account is not a unit test by most people's definition. But unlike these other suggestions, one advantage it has is that you are actually testing the integration between your code and the real external service. So don't fall into the trap of thinking that one testing philosophy or one testing tool can solve all of your problems. And just to emphasize that, let me quote from a piece of writing by Alberto Savoia called The Way of Testivus. This purports to be a translation of ancient Eastern wisdom about programming. It says, "Dogma is inflexible. Testing needs flexibility. Dogma kills creativity. Testing needs creativity." So today, I don't plan to lecture you on how you should test your programs, but I'm going to show you a few maybe surprising ways that you could test your programs. But that's enough wisdom. Let's get back to some code. We'll assume that we've already chosen one of those earlier methods for testing our function, and we've written a setup and tear down method accordingly. What then might the body of our test look like? Right, here we're using the unit test module that comes standard with Python. So we inherit from test case and we write a test method. What it will do is call the getLatestTweet function and then check that the result is what we expected. Now that's really easy. So let's change the problem. Imagine that we want to rewrite our function to be an asynchronous call instead. How many people here have used twisted? A lot of hands. If you haven't, then don't worry if the next few slides are a bit foreign. Just briefly, Twisted Python is a networking library that uses an event-driven approach to concurrency. The event loop controls the execution of the program. So let's say at some point it calls a chunk of application code that uses our function. At this point, our function would initiate some work, but it wouldn't wait for that work to complete. Instead, it would return a special object called a deferred. Now, this represents the final outcome. The outcome isn't available yet, but it will be at some point in the future. So if the caller wants to know that final result, what they do is they add a callback. And that's just an ordinary function. Here I've called it CB. But later on, when that deferred has completed, then the Twisted framework will ensure that CB is called with the final result, in this case, the tweet. So there are no blocking I/O calls, and everyone is happy. Everyone except me, because I have to write the tests. And the problem is that if I use the same approach as before, then when I call this new function, all I get back is a deferred. And what can I test at this point? What do I know about this deferred? I know nothing except it hasn't even been called yet. So I could do assert false on d.called, but that's obviously pretty meaningless. And in fact, this deferred won't ever be called because the event loop isn't running. And we could start the event loop running in our test, but then we'd have to worry about how do we stop it? How do we handle errors and so on? There must be a better way. And fortunately, the clever folk who wrote Twisted have provided some testing tools in a package called Trial. This includes a test case class that inherits from the standard one, but also manages our event loop for us. If we inherit from this class, then what our test method can now do is return a deferred, optionally. So we could return this, D, and now the test runner will wait until that deferred has completed before it marks the test as a pass or a fail. So if we do this, at least our deferred now will eventually fire. But what about testing that the result is correct? We can't put an assertion directly in this method, but we can add a callback. So the callback is just a function again. I've called it CB. It's just got that one assert equal inside it. And we can make this syntax look even nicer by using something called inline callbacks. To do so, we import this helper function, which we can also use as a decorator on our method. Then we write our method using the yield callback. The yield keyword. And what that does is when we yield the result of getLatestTweet async, which is a deferred, control leaves this method and it doesn't return again until that deferred has completed, and the actual result will then be assigned to the variable tweet. That means all we have to do is use assert equal as before. And so although under the covers, the way this method runs is really quite different to that first method, that first test we wrote for the non-twisted version, to you and I reading it, it looks very similar in structure. It's short and it's simple and it's easy to understand. So in this case, we've been very lucky. The tools to make testing easier were right under our noses. But it's not always that easy. Sometimes you have to look further afield. Sometimes you may have to write the tools yourself. At this point, we're finished with Twisted, but not quite finished with event loops, because I'm going to talk a bit about UI testing. UI tests, particularly for desktop applications with a graphical interface, have always been the scariest kind of test to automate. This point and click is so easy for a human operator, but it's difficult to automate. It's typically done by fabricating your GUI events, sending them to the application, And you can do that using code. There are also some tools around, particularly some commercial products I've noticed, that take a record replay approach. But once you get over this hurdle of actually automating your mouse clicks, you soon discover the real problem with GUI tests. They can be very brittle. Woe betide if your tests rely on some specific pixel coordinates, because GUI layouts change with surprising frequency. Hardly a build goes by without some widget being added or moved or resized. And so you may find yourself spending a lot of time updating your GUI test suite, fixing those tests when they break, or maybe re-recording your tests every time they break. One option that is tempting and can perhaps be justified on a smaller project is not to automate it all. And believe it or not, we actually found some ways to do test-driven development without full automation. Now, what you see here is a window from an in-house application. It's asking the operator for intervention in the process of standardizing the format of name. So the user will mainly interact with this frame here. It's basically a specialized name editor, and it has some quite complicated behavior attached to it. Fortunately, it's implemented as a separate class, and we would like to test this GUI component in isolation. Now here you see that component being used in a test. This is a scripted manual test. Instructions appear at the top, and the tester clicks yes or no in response to the question. So here the instruction at the top says, can you move Muhammad to the end of the name? This is actually a real use case because Muhammad is a very common given name. In some of the records that we've received, it may even be omitted. And so, strictly for our internal use in data matching, we prefer to make the other part of the name, Hassan in this case, more prominent by moving it to the start. So the tester would do this manually. They would change over the names and they would click yes, and then another instruction appears. This asks us to abbreviate Muhammad to MOHD. Now again, this is because the name may be abbreviated in some records, or it may be given a variant spelling, and so for our internal purposes only, we standardize it. So the tester would edit that field, and they would click yes again, and the test passes. All right, let's have a look at what the code for that looks like. Again, I'm going to omit the setup and tear down methods, but stealing an idea from the twisted test that we looked at earlier, this test also uses the yield keyword. And we've written a test runner for this that will display this string and and wait for the user to click yes or no. And control will only return to the method, the test method, after the user has clicked yes. After that, we immediately display that second instruction. But then at the end, we check the state of the component under test. And this is vitally important because the program might look like it's doing the right thing, but actually be saving the wrong data. So I call this a semi-automated test because there's no automation at the graphical interface, but there is verification at the programmatic interface. So the advantage of that is you can do test-driven design, writing your tests before the code. But once the code is complete, there's no way to run the tests again on every build. So you lose automatic regression testing. And that means that we weren't able to get the maximum value from our tests. But then we discovered an opportunity. One of the long-standing requirements for this system was that it be keyboard accessible. In fact, some of the components support quite complicated keyboard commands. And so, if anything, testing those commands was more important than testing interaction via the mouse. So we seized upon this as an opportunity to automate the UI. We converted those semi-automatic tests into keyboard-driven UI tests. We had to write a new test runner, but the tests themselves only required a small modification. So comparing to that earlier piece of code, the only change here is the two yield statements. And we've just added one extra string to each one that encodes a sequence of keystrokes. So the first one there, the MG1G2, just means send these 5 keystrokes to the component. And that's actually a single command that means move given name 1 to given name 2. So let's run that and see what it looks like. Okay, that is running at the normal speed with a 200 millisecond pause between keystrokes. I'll just play it again a bit slower. So first switch over the names, then edit to add the abbreviation. Of course, you'll usually want to run these methods headless so that they don't keep popping up windows on your monitor all the time, but I'm not going to get into that right now. But the nice thing I will say about using keyboard events is that it's actually a very stable interface. Unlike GUI layouts, keyboard shortcuts don't often change between builds. Now, this approach is not going to catch every kind of GUI defect. It's not going to catch any cosmetic faults. But in our experience, it can catch a large proportion of the more serious GUI bugs. Now, remember, I'm not claiming that keyboard-driven UI tests are the best approach for your project. What fun would programming be, after all, if there was no room for creativity? This is a specific solution to our specific problem, and it's very satisfying to find a lightweight design that gives you 80% of the value for 20% of the effort. Okay, what we've seen so far are tools that extend the capabilities of the basic unit test module. Now let's look at one alternative to that style of test. It's called FIT. This is a test framework invented by Ward Cunningham about a decade ago. He wrote it for Java, but it's been ported to a few other languages, and the Python implementation is called PyFit. Using this framework, the test cases are not written as code, but rather as text in a tabular format. This has some limitations, but it also has some compelling benefits. For one, it means that the tests are accessible to non-programmers. So it's particularly suitable for writing tests of your business logic, the things that your customer really cares about and understands better than you do. Another benefit is that these tests can be very concise. And that's great when you have a large number of tests that share a very similar structure. Now let's look at one. This is simply an HTML document. FIT only cares about tables. So between the tables, you can add whatever headers and explanatory text you like. And please forgive the gratuitous skeuomorph of the torn paper. But do notice that this is something you could print out and show to your customer and have a conversation about. That's not something you can easily do with a unit test written in Python. The first column is the input, the raw gname column. And the other two columns, notice they have a question mark in the header. That means that they're the output columns. And each row of the table is a separate test case. So I'll just step through the second row here. It's saying when the input is Muhammad Musa, the result in the gname should be those two words but as separate items in a list. And in addition, it should set a warning message. And that is what causes the program to ask the operator for manual intervention, just like we saw in that example with the GUI. But how does FIT know what test or what code to use to verify these test cases? Well, the first cell here provides a class name, and that's called the test fixture, and we'll have a look now at how that class might be defined. The fixture inherits from one of several available base classes, with column fixture being the simplest one. And this class must contain member variables matching the names of each column in the table. For each of the test cases, so for each of the rows in other words, fit will first set any input values, so just raw gname for this, and then it will call a method called execute. Here is how we might write the execute method. So you can see here that the part of our system that's actually being exercised by these tests is this function name_clean. That's what we're actually trying to test here. Now, after this has been called, fit will then compare the outputs, the gname and the warning message, to the expected values that are in the table. So, returning to this test now, if we run fit on this document, then the output will look like this. The correct results are shown in green. And at the moment, everything passes. But what if we decide we want to change these business rules? Remember, when we were testing in the GUI, we had to move the Muhammad to the end of the name and abbreviate it. Well, instead of requiring the user to do that manually every time, how about we make that an automatic business rule? Let's start by changing our tests. We'll have another look at the second row here. So now we're saying, when the input's Muhammad Musa, it should be changed to Musa and MOHD. And there should be no warning message. Here we have to use the explicit word blank to show an empty value. And if we run these tests, this is what we get. The disagreements between the expected and actual outcomes are coloured red. And only one cell is green, and that was more an accident than anything else. The next step, of course, would be to start changing your code so that your tests go green. Now, all the examples I've talked about so far have involved writing one or more test cases and specifying the expected outcome in each of these test scenarios. Well, this paradigm has a long history in software engineering, but it's not the only approach. Consider the difference between the assertions in those test cases versus the humble assert statement that you might put in ordinary code, hopefully as often as possible. Rather than describing what's expected in a particular scenario, the assert statement is expressing a condition that should always be true at runtime, no matter what the input values are. And there are some approaches that take this approach to design and testing even further. There is design by contract, popularized by the Eiffel programming language. There's also property-based testing, which has really taken off in the functional programming community. Quick check is an example of that approach. And you could even include something like load testing in this category. Because under high loads, you're not expecting some deterministic response from your system. You just care that it satisfies some sort of general property, like a maximum latency or average throughput, or just that it doesn't fall over and burst into flames. I'm not going to go into any of these in depth, although there are certainly tools in Python to support all of these approaches. But more important, I think, is just this seed of an idea that rather than expressing your tests as specific test cases, hard-coded examples, you can express them as general properties which the computer can evaluate. Now that's just another weapon to add to your testing arsenal. And to make that a bit more concrete, I do have an example. In our system, we have something we call a round-trip test. Our system, which is the new system, needs the ability to replicate data to a second legacy system. Unfortunately, the data schemas are very different. They are very different indeed. In particular, if we were to test just a single field, and test that in isolation, then it wouldn't give us confidence that composite data was also translated correctly. So instead of using a small number of fictional test cases, we wanted tests that we could drive using real data. Now, rather than inspecting the legacy system directly and trying to compare these different schemas, we found it easier to implement the translation in such a way that we could run it forward or in reverse. So during development, we can take some sample data, we can translate it into a test instance of the legacy system, and then we can translate it back again into a new, fresh test instance of the new system. And finally, we can compare the original data to the round-tripped data. And that's very straightforward because they share the same format. Now, in case all those arrows obscure the actual property that we're testing, let me write it here in a more equational form. If this translate function, which we can call t, has an inverse, which we'll call u, that's the untranslate function, then if we take any data and apply t and then apply u, then it should yield exactly the original data. So a successful round-trip test is showing us that this translation is reversible. But how does that property actually help us? Well, the most important thing it shows is that no information is lost or becomes ambiguous in this process of translation. Because if so, how could you possibly recover it, no matter how clever your untranslate function is? Now, this property does not necessarily, or doesn't prove at all, that the translation is the correct one for the domain. But we have other tests to address that. What the round-trip test does do in our experience is it catches some things, some common defects that the other tests don't. Things like omitting a field from the original spec. So we've certainly found these useful, and even after deployment, we still run these tests once a week, after hours, using the latest production data to verify that there are no anomalies in the new data that might affect the translation into the legacy system. Now, I'm afraid I haven't left much time for, I have left a couple of minutes for questions. If you want to try any of these ideas in your own project, then do feel free to contact me. If I can help out with some sample code, I'd also be more than happy. So may the weapons you choose for testing be sharp and shiny, and thank you for choosing my talk today.
If you would like to ask a question, there are 2 microphones at the base of the stairs here. Please queue and we'll try to alternate between.
Hello. Thanks for your talk. It's really great. What I wanted to, going back to the twisted stuff, I haven't done a lot of twisted, but in the one-liner that you had there with the yield function, given, from what I understood, it would run the test, get to the yield function, go off, run a bunch of other tests, and then once the yield function came back,
okay, I'll interrupt. No, the one test case will wait until all the deferreds have fired.
Right, okay.
And then it will decide whether it's a pass or a fail.
Right, okay, cool. Because I was thinking if you've got like stuff going into a database or something, and there's all these tests running all over the place, then but it just stops in that test and waits for the deferred to come back, and then does the assert. Yeah, and ordinarily, I mean, generally your test should be quite fast. It's just more a matter of how do you wire these deferreds together and so on, which then the test framework can handle. But you can also set a timeout, and there is a default timeout. So one way your test could fail is that the framework is waiting for 30 seconds and it doesn't finish. Right. Cool. Thanks.
Hi. You had a one-liner there on load tests, and you didn't otherwise mention them. I'm particularly interested in them. Methodologies about doing load tests, what counts as pass, what counts as fail, how you know how much load to generate, things like that. Do you have any kind of thoughts on that?
My suggestion is that you wait in this room for about 5 more minutes, because I think the next person is talking about, I think the next talk is on that sort of topic. Next one after.
Oh, okay.
Okay. As a matter of fact, I don't work in the web development space, and so I don't really have any opinions on that load testing.
Okay.
I actually have a question. Outside of the web space, back in the day I used to do GUI testing, and I'm intrigued that you've got, your testing system has got this human in the loop aspect. You said that, you know, capturing the events and generating events is one way of simulating what's going on, but then that doesn't test that the widget has been shown in red and that it is on the left-hand side of the screen, which is the thing that ultimately is the hardest thing to check without doing image diffs or something like that. And then you've gone and put a human in the loop with a pressing a button, and then the human, again, more often than not, like I remember having an application that had a 100-page manual test suite, and by the time you got to page 75, it was like, yes, yes, yes. You end up getting false positives because the human is a bad tester.
Right.
So yeah. How do you factor that into your testing regimen?
Right, and see, that's why I mentioned that we used those tests for doing development. So we would write those tests first, and then when I say tester, I want to emphasize that it's a human operator. But in this case, the tester was always the developer, just writing the code. They would run the test, see if it passes or not. I certainly agree with you that using that as some kind of deployment or customer acceptance kind of test, well, we don't do that, basically, and we stopped at just automating via the keyboard, because that's good enough to capture the serious kinds of bugs, like when some widget just stops working, then we'd like to know about that. And we don't have a lot of users. We're just doing in-house applications. So when something is supposed to be read and it's not read, then unfortunately it comes back to what I think was mentioned in the keynote. Someone complains, and so we fix it.
Actually, I was intending to ask a very similar question, and it seems you've actually answered my question. But so you have never really seriously considered the costs of actually putting non-developer people to, I guess, be the human bots to sort of automate that level of testing then?
No, we don't. I kind of feel that I would like to experience that style just to see how dysfunctional it is, because you know, the Agile people call it waterfall, and yeah, we've never had manual testers, no. Have you any experience with that?
No.
How many people here work with a tester or do consider themselves a tester? All right, so there are quite a few.
Just a quick question on that. Have you come across this product called Sakuli?
No. What's it do?
It's a Python scripted image tool for testing GUIs. So instead of clicking that point on the screen, you define this is what the thing looks like that you should click on, and it clicks on the button that says OK, regardless of where that is.
Right.
So it's a Python scripted tool.
That, I think I saw a commercial product that was similar as well.
It's not commercial, so.
And I think that is, from a technical sort of mindset, that sounds really clever.
Yeah.
Yeah, and it should reduce the number of things that you have to redo or fix. But the problem with this record replay approach is what you tend to end up with are tests that are just, you know, they are not well factored, because you have, you know, 20 different tests for this particular page maybe, and they all involve first doing one thing and then testing something else. So they all have the same sort of setup that becomes part of that script. And when that original bit of setup changes somehow, you know, there are different drop-down options or something, then all your 20 tests break. And so, I mean, that can also happen with coded tests for sure. And the solution to that is better factoring, and to factor out the shared part of that code. And I'm not sure if the record replay tools have equivalent sort of functionality.
Okay, thanks very much, Todd.